Hello everyone. In today's lecture, we are going to see the energy concepts related to excitation, mostly harmonic excitation of a single degree of freedom system. We are going to look into how the energy transfer takes into place. So, how much of energy is being input in the system, and if it's a damped system, then how much of that energy is being lost through that damping or the energy dissipation. Okay, we are also going to see how to obtain the equivalent viscous damping for a damped system. Okay, now as you know that viscous damping is not always a realistic mechanism, okay, for any structure, but what it provides us a linear damping model that is suitable for mathematical solution purposes. So we prefer to use viscous damping. So we will see that today as well how to actually equate a system that has viscous damping to a realistic system and how to obtain the coefficient of viscous damping.
Okay, so till now we have been studying basically how to find out the solution to this equation subject to this type of harmonic excitation. Okay, now what happens in many scenarios that in order to apply this harmonic load, okay, it can be applied either using a motor which is constantly vibrating at frequency omega t or the frequency omega, okay, with amplitude p naught, or it might also be applied with, let us say, an actuator in a laboratory. Okay, now if you look at it, an actuator is nothing but a device that is used to apply load for, let us say, we have a column here, okay, and we can apply what kind of displacement history or load history we want to apply through this actuator. Okay, now it might not always be possible in a laboratory setup to apply huge excitation or harmonic excitation using these actuators. Okay, so what we are going to learn today, how to apply basically harmonic excitation using vibration generator. Okay, now these vibration generators, okay, it could be a deliberate design to actually produce vibration to a structure, okay, and the practical example would be where you would actually like to find out the modal properties, okay, using the vibration generators. And other could be cases of unbalanced load. For example, if you have a rotating machinery, okay, and if its unbalanced load is there, then it would apply some force. Okay, a very common example that many of you see in your houses is actually if you have, let us say, a washing machine. Okay, so many of the washing machine now they have, like, come up with different technology to balance the load, but usually what happens, due to clothes rotating inside, the mass distribution is not symmetric about the center, and that leads to unbalanced load, and consequently, due to the frequency unbalanced load, there is a basically load that is applied to the supports here. Okay, and that you can observe in any situation, any common scenario where the washing machine is being operated. Okay, or we could actually design a vibration generator in which, for example, let us say here, okay, I have two rotating masses, okay, which are vibrating about, so these are connected through a common sleeve here at the center, and these are rotating at an angular frequency of omega, so that after time t the angle traversed through these masses are omega t, and let us say the masses are m by 2 and m by 2. Okay, and let us say this radius here is r. Okay, so as we know, if we have a mass rotating about a fixed axis, it would apply a certain centripetal force. Okay, so if this mass is rotated, it would apply a centripetal force which is directed along this radius, and the magnitude of that centripetal force is actually m by 2 omega square r. Okay, basically mass times the square of the angular frequency times the radius of rotation. Okay, now if you look at it, the system here, the horizontal component of these centripetal forces are going to cancel off. However, the vertical components are actually going to add up. Okay, so if you take the vertical component, it would be sine omega t, and plus, of course, for the second mass, same expression would be there. Okay, so net vertical force, net horizontal force is actually equal to 0, but net vertical force is this, which is nothing but m omega square r sine omega t. Okay, and basically the rotation is actually through an external source. Let us say it could be a source like an electricity source, a motor that applies these rotational velocities to these two masses. Now, what happens if you take this rotating setup of unbalanced load, okay, and if you attach to any kind of a structure, okay, if you attach to any kind of a structure, let us say here, okay, what will happen? It will, depending upon at what frequency it is operating, it will apply this much of excitation. So if you consider something like this, P naught sine omega t, okay, if you attach this vibration generator to any structure, it would apply the same amount of force to that structure, and then the response of that structure subject to this excitation force can be found out using the conventional methods that we have discussed previously. Okay, except there is one small difference here. If you see, P naught now is m omega square r, okay, which is a function of excitation frequency. So initially, remember when we had P naught sine omega 2, P naught was independent of any excitation frequency. Here it is a function of the excitation frequency. So as we increase the excitation frequency, our amplitude also increases. Okay, and that is also the reason we cannot apply a very small amplitude load here. Okay, or we can say like we cannot apply a load statically, because to apply a load statically, I have to have the frequency omega, which needs to be very, very small. Okay, so for static, I need to have omega very, very small, and that would lead to P naught, which is very, very small. So the P naught would be very small, so the response of the structure would be like very small, or like it cannot be realistically measured. So that's why it is difficult to apply static load using this method of vibration generator. Okay, now given that it depends on the excitation frequency, let us find out if I attach to a structure and that structure is now being idealized. Okay, for example, let us just leave it here. Okay, let us say this is now being idealized as a spring mass damper system. All right, okay, and with mass m, all right, and to which I'm applying P, that is equal to m omega square r sine omega t. Okay, so do not confuse between this small m and the capital M. Okay, the response that need to be found out is for the capital M. Okay, but the excitation frequency is applied using this small m. Okay, so in this case, the ut would be found out as u naught sine omega t minus phi. Okay, now if you look at here, u naught I can again obtain as Rd times the static displacement, which I can further write as P naught by K. Now in this case, P naught is m omega square r divided by k times RD. Okay, so U naught would be m. Okay, so I can write U naught as, if I divide this by m and then multiply also by m, okay, I can write mr by m times omega by omega n whole square times RD. Okay, so for a frequency dependent force, okay, for a force whose amplitude is actually frequency dependent, okay, like in the case of vibration generator, this is the expression that we get for peak dynamic displacement. All right, now similarly we can also obtain the expression for basically the acceleration. Okay, now as you know, acceleration u naught is actually p naught by m, okay, times omega by omega n square, okay, times r, or let me just write here p naught by m times ra, okay, where ra is acceleration modification factor. Remember, these all comes from the previous classes that we had discussed. If you remember, basically you had ut by p naught by k is equal to rd times sine omega t minus phi, okay, u dot t divided by p naught under root km is actually rv cos omega t minus phi, and the third expression was for acceleration, which was p naught by m minus, okay, this was ra here, so this equal to ra sine omega t minus phi. Okay, so basically we are using the same expression. The amplitude here for u naught would be p naught m times ra, which I'm writing it here. So I can further write this as m omega square r. Remember, this would be capital M here because the mass of the single degree of freedom system is actually capital M. So just keep that in mind. Okay. So what I would have here is capital M again times RA. Okay. And if I'd like, I can further write this as M R, okay, omega n square divided by capital M times omega by omega n square RA. Okay, so the variation of u naught and the acceleration, okay, u naught double dot, would actually, if you try to plot it, now it would become a divergent function. Okay, so let us say I'm trying to plot here u naught divided by mr omega n square by m. Okay, it will start from a value of 0. For a very small value of damping, it would look like something like this. Okay, so it would look like something like this because I have RA, which used to approach to 1 for large value of omega by omega, but now it is multiplied with omega by omega n square. So now at large value of RA, it actually approaches to infinity. Okay, now the question becomes, where do we actually use these kind of things? So we utilize vibration generator, as we discussed, to provide harmonic excitation to different type of system, okay, which are usually not possible using actuators in a laboratory setup. So let us say, and this actually has been done, let us say our goal is to apply harmonic excitation to a structure like multi-story building which is outside and or like a big dam that is there. So I cannot take an actuator and even if I wanted, I could not apply that kind of force. So what I do, I apply, and in this case I need to attach this vibration generator to either building or the dam, and then keep increasing the frequency, and we'll see that at certain frequency, okay, the response will start to gradually increase. Okay, and that is basically the time period of the or the natural frequency of the structure if the damping is very small. Okay, so that is basically a beneficial use of vibration generator. In many cases, you have unbalanced machinery. For example, let us say, we talked about washing machine. Okay, I could have an air conditioning unit which is like, supported at these 2 points, or it is supported to, let us say, wall, and then again it is rotating. Okay, so there are different applications of this kind of vibration generator. Okay, now we utilize the vibration generator to find out, okay, what is the modal properties. So we want to find out omega n and damping in the system, and for that, what do we do? Actually, we perform using this vibration generator. Okay, we apply the excitation. Now if you remember, for damping, okay, for sorry at resonance, if you remember, for a small value of zeta, I could write as u naught by ust is equal to 1 by 2 zeta. Okay, for small value of damping. Okay, now the easiest way to find out damping is to find out, okay, remember this u naught is basically at frequency omega equal to omega n. Okay, so zeta I can directly write as ust naught divided by 2 u naught omega by omega n. So let us say, okay, let us say if I can find out what is the amplitude, okay, at frequency omega equal to omega n in the system, okay, through this vibration generator. Okay, so then, and if I can find out ust naught somehow, then I should be able to obtain zeta. The problem with that is we do not a priori know what is the value of omega by omega n. Plus, as previously described, it is very difficult to apply static load using vibration generator. Okay, so in realistic situation, what do? We actually obtain frequency response curve. Okay, so basically we obtain frequency response curve. Okay, in which what do we do? Okay, we, let us say, rotate this vibration generator, okay, so that it applies at certain frequency, okay, to a structure, or it could be like any type of structure, but let us say we are considering a single degree of freedom system. Okay, so let us say this load is being applied to the system here. Okay, when this load is applied, we can find out for this frequency omega n. Okay, and remember for this structure omega n is fixed. Okay, I'm only varying the excitation frequency. I can find out what is the peak response. Either I can do it in terms of displacement, or I can do it in terms of acceleration. Okay, so I do it for one frequency omega n, then I again rotate the same machinery at different excitation frequency. Okay, so let us say it is a higher frequency. Okay, and then again I do the same thing. Okay, I measure what is the peak response, either in terms of, let us say, displacement or acceleration. Usually what happens, acceleration can easily be measured using accelerometer in a using instrumentations, and in many cases finding out the displacement is a little bit difficult. Okay, so we measure actually the acceleration. Now remember, for all these cases, my acceleration is for the force amplitude, right? That depends on the excitation frequency. Okay, so in order to find out the acceleration that is independent of the frequency, of the force amplitude, we divide it by that frequency. So we divided by omega n square, we divided by omega 2 square, so that whatever we get is actually independent of the frequency. All right, and then we do it for several such excitation, and then we try to plot, okay, the response, okay, and see the variation. Okay, once the variation is obtained, remember this is omega by omega n. Okay, once the variation is obtained, okay, then we can go ahead and use the half bandwidth method. Okay, half bandwidth method, where we apply r, this is r by root 2, and then this is, let us say, omega a and omega b. Okay, using this method we can find out the damping. Okay, formula you already know, it is omega b minus omega a times omega b plus omega a. Okay, and either you can directly find out the frequency here, okay, omega by omega n, at which your response is maximum. Okay, or you can take average of omega a and omega b to find out the omega n. Okay, so these techniques can be employed without having to find out the UST naught or the response at the maximum value of omega n. So using this technique, okay, experimentally we can find out the modal properties. All right. Okay, once this is clear, let us move on to the next topic, which is basically, as we discussed, we need to measure in laboratory acceleration, displacement. So the question comes, how do we actually measure it, and what instruments do we use, and what are the principles behind those instruments? Okay, so the first thing that we are going to discuss is in vibration measurement instrument. Okay, vibration measurement instrument, we are going to discuss acceleration measurement devices. Okay, many times it is commonly called as accelerometer. Okay, so we'll first talk about acceleration measurement. Okay, now acceleration in the laboratory is measured using, as I said, something called accelerometer. Okay, in its simplest form, an accelerometer is nothing but a spring mass damper system, okay, which is inside a small rigid box. Okay, and this box is something like this. Okay, and if I have to measure acceleration to any point on the structure, all we do, we just take this small box and then connect it to that, rigidly to that surface. Okay, so this provides us whatever the acceleration of the connecting point. Okay, and how do we do that? Let us see. Basically, let us say if it is connected to even a top of a structure like this. Okay, so let us say it is connected at this point. Okay, so in terms of excitation, it is nothing but, okay, a spring mass damper system. Okay, so I can further rearrange this, and I can write this as, let us say, support excitation in terms of UG of T. Okay, so this system is basically like that. It doesn't matter which point you attach this accelerometer to, this point, it is basically a spring mass damper system being excited through a support excitation. Okay, and this is a representation that we have been discussing till now. Okay, now we know that for this case, our UT can be written as, okay, UST naught, all right, times RD sine, okay, omega. Okay, this is not omega n, this is omega t minus 5. Okay, and excitation basically is in the form of UGT is equal to, okay, Okay, so this is acceleration here. It is in the form of UG t times sine omega t. All right. Now, you might argue that the actual response here is support excitation is not harmonic, and I completely agree with you. But like we have previously discussed, even if you have a random excitation like an earthquake, okay, it is made up of several such frequency. Okay, right. So the goal here is that if we can understand or find out the response to one such frequency, okay, and then combine all those frequency, okay, then we should be able to find out the total acceleration at that point. Now, if you look at here, okay, so I want to devise an instrument which is giving displacement history like this. Okay, I can further write this as, remember, UST naught here is nothing but P naught by K, which is minus M times, okay, UG double dot, or I can write this as UG naught divided by K. Okay, so this can be written here as minus M divided by K RD, and this is UG naught omega t minus phi. Okay, oh, the sign term here. Okay, now this expression is nothing but UG t minus phi by omega. If you substitute the expression here, you will see in this one, okay, that you will get the same expression. Okay, so if you substitute in this expression, let us see, okay, sine omega t minus phi by omega. Okay, this you get as sine omega t minus phi. Okay, so basically this is the same expression is this, okay, for a time variation t minus phi by omega. So I can write this expression, okay, I can write the expression for ut as minus omega n square rd, and this as t minus phi by omega. All right, now if you look at this expression carefully, okay, this is what we want to measure, isn't it? We want to measure at whatever excitation, okay, the support is being going through. Okay, so we want to measure the support excitation. Okay, so the question is, how do we do that? How do we measure the excitation? So that support excitation actually is nothing but the displacement, okay, multiplied with some factor. If you take like, these factor RD and this, okay, and with a phase difference of phi by omega. Okay, now we can say that in this case, okay, that my ut right now depends on the frequency. Okay, so the displacement actually is depending upon the frequency. Okay, because RD also depends on the frequency, and phi by omega also depends on the excitation frequency. So if I design this instrument, it would give me different values of phi by omega and the value of RD. Okay, but I won't be able to sum those up. Okay, so if somehow, okay, if this term here and this term here, let us say, are independent of, okay, are independent of the excitation frequency, then the instrument would provide me, okay, different values, let us say omega 1, okay, due to a frequency, okay, omega. So I can write this as minus RD time omega n square. Remember, RD depends on the omega 1 as well, times UG1, okay, which if it is independent of omega, I can again write this as t minus phi, and RD is also independent of omega, then I can write it IRD. And ut again I can write it like that. Okay, so I'll have several things, and the total response I can sum it as u1 t plus u2 t and so on. Okay, so the instrument the accelerometer should be independent of the frequency that it is being excited. Okay, so it is like, goal is to design an instrument such that to make it independent of RD and phi by omega. Okay, because then each harmonic component we can record with the same modifying factor, the RD by omega n square. Okay, and with the same time lag. Okay, so even in that case, if my earthquake excitation consists of, like, many harmonics, okay, we can record the ut, okay, with the same shape as the support motion. Okay, so the shape of the function would be same if it is independent of that. Okay, so all it would need is that a constant factor times this RD. Okay, and that constant factor can be found out as instrument factor of the accelerometer. Okay, so this is our goal: make RD, okay, and omega phi by omega as independent of the excitation frequency. Okay, and that we can do if you remember the plot for RD, okay, and phi by omega. Okay, if you remember, for different value of damping, it look like this. For very large value of damping, actually it started to become like this. Okay, similarly, this for zero value of damping, there was a sudden rise 0, let us say 90 and 180, and for large value of damping, it was almost like this. Okay, so what do we see? That if my damping, okay, is 0.7, okay, and omega by omega n is smaller than 0.5, okay, if it's smaller 5, and if this curve here, let us say middle curve is zeta is equal to 0.7, in this one as well, okay, let us say this is 0 1, okay, if I consider that, let us say the middle curve is zeta equal to 0.7. Okay, for these conditions, okay, my RD is approximately equal to 1, and phi by omega is actually linear. Okay, or I can say in this case it would be almost equal to a constant. Okay, so it's a completely straight line. Okay, so if that is the case, then what will happen? This would be another constant and this would be 1. So all value of displacement, okay, if you remember the expression here, okay, let me write this as like this. Okay, if this is phi by omega 1 is equal to actually linear, then phi by omega would be a constant. Okay, and RD is equal to 1. Okay, so then whatever the support excitation is actually the displacement that is measured. Okay, and now let us say I have this spring mass system. Okay, and there could be a, like, a digital recorder, or it could be like, simple paper recorder. Let us say this paper is something like this. Okay, and let us say I have this system here. Okay, and the excitation is, let us say, being applied here. Okay, so what happens as you apply the excitation, and this, let us say, this is a paper roll here. Okay, so as it vibrates, it would actually record its displacement here. Okay, and if this single degree of freedom system satisfy this condition, then the same displacement, whatever we are recording here, can be converted to acceleration. It is actually acceleration. Okay, all right. Okay, so in this case, we can measure it like that. Okay, and that is the basic principle of an accelerometer. All right. Okay, now let us move on to the final topic of this chapter, which is basically energy calculations in damped harmonic motion. Okay, so we know that for viscous damping, okay, we had represented our FD, or the damping forces, C times the velocity u dot. Okay, and we also know that the energy dissipated through any force is basically force times the displacement over, and the integration of that basically over a certain time. Okay, so if I want to find out what is the energy dissipated due to my viscous damper, okay, I can write this as Fd times du over any certain time t. Okay, and let us say I want to find out Ed over a cycle, okay, during steady state harmonic motion. So I'm only focused on steady state harmonic motion. Okay, in that case, over a period, it would be 0 to t, okay, times Fd times du. All right. Now this t is basically, I can further is 2 pi by excitation frequency, 2 pi by omega. Fd, I can write it as cu dot, and remember du, the small displacement, I can also write as u dot times dt. So my expression becomes c u dot square dt. And u dot I already know, well, u I already know as u naught sine omega t minus phi. Okay, we can find out u dot as u naught omega cos omega t minus phi. Okay, so we can substitute this expression, okay, here as c u naught square omega square cos square omega t minus phi, okay, dt, and integrate it over this. Okay, if we integrate this, you'll see that the expression that you get is pi c omega u naught square. Okay, so this is the energy dissipation over a single cycle during steady state. Okay, this expression can also be written as, okay, if you substitute the value for the damping coefficient c, okay, this can be further written as 2 pi zeta omega by omega n times k u naught square. Okay, if you don't remember, we had defined our damping, or the damping ratio, as C by C critical, which I could write as C by C critical is like, I can write this as 2k by omega n. Okay, so C I can write as 2 zeta, okay, k divided by omega n. So basically I just substituted it here to get this expression. Okay, what is the utility of this expression? We'll see later. Okay, so remember these two expressions, and these were simply arrived by considering Fd and integrating it over a certain time, okay, to find out the total energy dissipation. Now, I want to know that with respect to the, remember that it is a forced harmonic motion, so even at steady state I am basically inputting energy into the system. Okay, basically how I'm inputting energy into the system is it through p naught sine omega t. Okay, and I want to see where is that energy going. Okay, so let us find out how much is the energy that is being inputted into the system during a steady state. Okay, so I can find that over a cycle. Okay, supposed to be 2 pi by omega, right? And I can write this as pt times du. okay, which I can write this as P naught sine omega t, and du I can write as u dot times dt, okay, which I can further write as u naught omega cos omega t minus phi times dt. Okay, and you can integrate this expression over the limits, and then you can find out what is the final expression. I'm just going to write it as a P naught u naught times sine phi. Okay, and if you remember, the expression for tan phi was 2 zeta omega by omega n times 1 minus omega n by omega n square, correct? So sine phi is basically nothing but 2 zeta omega by omega n divided by this expression square, okay, for this square and then this square, which is nothing, denominator is nothing but what? It is RD value, isn't it? So this is omega by omega n times RD here. Okay, so I'm going to substitute there, okay, the expression for RD and see what do we exactly get. Okay, so if I substitute it here, I will get this as pi p naught u naught times 2 zeta omega by omega n. All right, and RD is nothing but u naught or dynamic amplitude divided by UST naught, which is P naught by K, right? So I can just cancel P naught, and this I would get as 2 pi zeta omega by omega n times K u naught square. Now compare this expression to the expression we had got earlier. The energy dissipated in viscous damping over a cycle is same as the energy that you are inputting into the system. Okay, so what does it mean? Well, in steady state, when steady state is achieved, okay, during the forced harmonic response of a damped system, whatever the energy that is dissipated in the viscous damping is actually the energy that is being inputted into the system. So that's why all the energy that you are inputting into the system, it's being lost into the damping. So whatever the amplitude you had achieved by the steady state, okay, that would continue. Okay, so there won't be any change in the amplitude of the motion at the steady state, and this is also the reason why it is called steady state. Okay, so the input energy is actually lost in the viscous damping. All right, and amplitude remain constant. Now you might be curious about that, what happens to the spring energy, the internal energy, which is basically ES. Okay, so remember, even at steady state, your spring is undergoing deformation and then mass is undergoing velocity. So they would have the potential energy, which is basically the spring energy. I can write as FSTU, okay, which I can further write as KU times U dot dt, and you can substitute again the expression for these, all right, and then integrate it over 2 pi by omega. Similarly, the kinetic energy, you can write it as okay, so this is A by EK, Fi times du. Fi is basically the inertial force. Okay, and if you want to find out over a cycle, again you can write this as mu double dot, all right, mu double dot times u dot t. Again you can substitute this expression and integrate it over the limits. What you are going to find out that these expressions are 0. Okay, so what do we see? Actually, that over a cycle of vibration during the steady state, the change in potential energy, okay, or kinetic energy are equal to 0. Okay, so that is what happens during the steady state to the change in the energy of the spring or energy of the basically the kinetic energy of the mass. All right, now let us have a look at that. We said that our damping force is represented as Cu dot, and this is of course a linear viscous damping that we have assumed. I want to have a look at how the variation, I know variation, how the variation would look like if I draw it with respect to velocity, right? This is FD and this is U dot. The variation would be linear, right? So that's why it is called linear viscous damper. Okay, but I want to see what happens, the variation, if I consider with respect to displacement, because displacement you can easily visualize, right? It is going from initial displacement to its maximum displacement and then oscillating about its equilibrium position. Okay, so I want to find out that relationship FD and the displacement U. So let us see how do we do that. So we are going to draw the graphical representation of FD. Now this is equal to C U dot T, which I can write it as C omega U naught. This would be cos omega T minus phi. Okay, and this I can write this as U naught, and cos omega t minus phi I can further write is as 1 minus sine square omega t minus phi under root. Okay, and if you remember, this is nothing but ut divided by u naught. Okay, so I'm going to take this term, okay, here, okay, and this I'm going to square it so that I get this as, okay, and if I rearrange these terms, okay, if I rearrange this term, let us write this one first. Okay, this is nothing but the equation of an ellipse. If you remember, the equation of an ellipse looks like form something like this. Okay, so this looks like an equation of an ellipse. Okay, so if I try to plot, okay, FD versus U, okay, remember the intercepts are basically whatever is the denominator of those respective variables. Okay, so it would look like something like an ellipse with intercept on the x-axis. This one as the coordinate would be u naught 0, and this coordinate here would be 0 c omega u naught. Okay, and what would be the total energy dissipated here? It would be FD du integration, which is basically the area under this curve. Remember, this was the expression for the energy dissipation, right? So the area under this ellipse is basically pi times the first intercept, let us say u naught, times the second intercept. So it comes out to be pi c omega u naught square. Okay, which is the same expression that we had earlier derived. So even through the graphical representation, we are getting at the same expression. Okay, now in reality, what happens, okay, when we have a structure or any element, okay, so even if we have like, something like this, we said that, okay, when we apply force on this frame, okay, it can be represented as a mass spring damper system. Okay, so we said that the damping and the stiffness, okay, this structure would have some damping and stiffness, okay, and the total mass was concentrated here. So in general, any structural element would have some stiffness and some damping, okay, small or high depends on the element itself, but it would have some damping. Now if you know, basically the Fs versus U for a linear system, it is basically simply a straight line. Okay, so in reality, what happens that when you measure, okay, especially in experiment you do not measure like, so if you take a component, let us say column, and you start applying a force, okay, and you start measuring like, the force behavior, it would be basically the sum of this spring force, okay, so this is here, okay, sum of the spring force and the damper force. Okay, so basically sum of these two forces, and which would look like something like this ellipse rotated by this straight line, which would look like something like this. Okay, so it would look like something like this. Okay, and how the curve would look like, how smooth it look like, depends on the actual behavior of the structure. Okay, so this is the total force, in that structural element versus U. Okay, if it's a non-linear element, okay, what you might see actually is that, okay, it might also look like something like, this. Sorry, let me draw that again. Okay, this is called viscous behavior and this is called hysteretic behavior. Okay, whether it would look like this on this depends on the element properties, but for our cases, our assumption is that it looks like something like this. All right, and this you can observe when if you have to perform experiment at some point, you will see that your force deformation loops for a regular structural member would look like something like this. Okay, so the question comes, in many of the situation, it won't be actually something like viscous, it would be like a hysteretic damper. Now for this system, I know how to solve for the viscous, linear viscous damping. I know how to obtain the solution. We have analytical solution available. Okay, and it's much easier and computationally efficient, okay, if I can somehow analyze or simplify this system to this without losing too much of accuracy. Okay, so for that, for those situations, we do something what is try to find out the equivalent viscous damping so that I can represent a system of a very general, okay, force deformation loop, something like this, okay, to a viscous damping like this. So for this, what I need to do, I need to find out a stiffness at certain value of displacement. Let us say this is the displacement amplitude. Okay. All right. So we need to find out, and then what do we do? Whatever the energy that is dissipated in this random loop, we equate it to a linear viscous damping loop that we had obtained here, okay, using our own formulation. Okay, so let us say we get K from, so this is what we got from experiments and we want to idealize this to this. So once we got this from experiment, we can find out what is the K using these points, okay, here and here, extreme points, and we can find out how much is the energy dissipated in one loop. Let us call this as ED. Okay, so the way to go about this is, let us say in this case, again have the same thing, and I am representing this as, okay, E, okay, the damper, the energy dissipation in the damper. Now in this situation, okay, basically what I'm doing, whatever the energy dissipation I get from the experiment, I'm equating it to the energy dissipated in a viscous loop, which is nothing but, remember, there is no energy dissipation in this linear, okay, elastic linear behavior of the spring. So whether it is rotated by an angle, doesn't matter, the total energy dissipation is going to be same. And I'm going to use the second expression, which was 2 pi zeta omega by omega n k u naught square. Now if you look at it carefully, okay, if you look at it carefully, this is nothing but twice of the strain energy, right? Twice of the strain energy. Okay, so this is here is ESO. Okay, twice of the peak strain energy of the system that we get from the experiment. So this can be further written as 2 pi zeta omega by omega n, okay, 2 times ESO. So zeta I can, okay, write it as 1 by 4 pi zeta times 1 by omega n times ED by ESO, where ED is the experimentally determined value of energy dissipated in a single loop here, okay, and ESO is basically the strain energy that is calculated using the effective stiffness and the amplitude. Okay, if I can find this out, I can represent this system using the system that we have derived all the equation for, which is the linear viscous damper. And how did we do that? We did that by equating the energy dissipation in this linear viscous damping system to the experimentally obtained energy dissipation. Okay, and typically what happens when we perform the experiments, we usually do it at the natural frequency of the structure. Okay, so in this case what we do, typically it is obtained at omega equal to omega n, and this case it could be written as ED divided by ESO. Okay, sorry, this is not, I need to just correct here. This is actually not 2 pi zeta. Okay, the value here is actually 1 by 4 pi 1 by zeta naught times this expression here. So no zeta here. All right, and this, I mean, this is very famously used in, like, many of the equivalent linear analysis. Equivalent linear analysis, we mean that when we actually have in reality we have a non-linear system, but we want to equate it to a linear system so that it is amenable to analytical solution and it is more computationally efficient. We utilize this expression to find out the equivalent damping. Okay, equivalent viscous damping. All right, so this finishes up the last topic, okay, of this chapter, which is the forced harmonic motion. Okay, next class we are going to start a new chapter. All right, thank you.